So today we are going to talk about Bell's inequalities, and the question is simply this: if you take this EPR experiment, for example the Bohm spin version of the EPR experiment, can you find some simple underlying microscopic theory in the sense of Einstein-Podolsky-Rosen, some realistic theory where you can think of properties even before the measurement? Can you make that work? This is the question. Now there's a word, people would call such a theory a hidden variable theory, because it would contain more variables than quantum mechanics, and they would be hidden in the sense that in experiments, then again, you can't measure both position and momentum, but they would be there and they would be part of the theory. Also, notice this is relatively modest. We don't even want to find a hidden variable theory to explain all of quantum mechanics. We just want to find a simple theory that explains this specific experiment, only a single Gedanken experiment to be explained. We don't worry about whether it's a general description or not. Okay, so when you face such a question, you don't try to prove something general at first. Rather, you will just try the first simple model that comes to your mind, and if that fails, you will try the next one. If that fails again, maybe you start thinking of why it fails, and then in the end you might arrive at something general. So we start, just like Bell did, with a very simple model. And what could be the simplest model you have in mind? Well, remember, we just have these two particles with a spin, and if we measure the spin, it can be either up or down, regardless of the direction we measure. It can only have the two values up or down. And so, what would be your picture, your classical-like picture of such a situation? Well, at least I imagine a spin is like a little arrow, a little vector associated with a particle. And probably the singlet state then should be like one arrow pointing in one direction and the other arrow pointing in exactly the opposite direction. Yeah, so let's just draw this situation. And let's call this our first attempt. So we have these two particles that are emitted from the same source. And then I would just pick a spin direction for particle number A, and the opposite spin direction for particle B, because we already know the singlet state has this property that if one is up, the other is down. Now, this cannot yet be quite the correct model, because we also know that the singlet state is isotropic. There is no preferred direction. I can measure in the z direction, both of the particles get opposite spins. I can measure the x direction, also get opposite spins. So I should also make a model that is isotropic. Now, unfortunately, this particular situation, of course, has a preferred direction, namely this one, which I picked. But I can just claim that the source in here will then randomly pick such a direction each time it emits this pair of particles. And it's randomly distributed uniformly over the sphere, so that in the end all directions are equal, statistically speaking. That will be the idea. So just pick a direction, but pick it randomly each time, and pick the reverse direction for the other particle. So our spin is just represented by a direction, which is a unit vector. And we will call it lambda, vector lambda. So that would be lambda, And this here obviously minus lambda. Okay, and lambda should be randomly distributed. So this is our best approximation that at the moment we can come up with for the singlet state. Then there's something else. We have to talk about the measurement. So what does the measurement mean? It means that both for A and B individually we pick some measurement axis. Let's call this vector little a and vector little b. And then we, in the real experiment, would have a Stern-Gerlach apparatus to actually measure the spin along this direction, and we know it can only have two values, up or down. So for our particular model, we have to invent a prescription of when will the result be up and when will it be down. We can't just say, oh look, the spin is neither up nor down, it's somehow tilted. This is not a valid answer, because in the real Bohm EPR experiment, only up or down are allowed answers. So for our little classical-like model, we just have to invent a prescription. And I don't know about you, but the prescription I would invent is, if they are mostly parallel, like this, then I would say it's up. So for this situation, I would call it up. If they are pointing in the opposite directions, sort of, then it should be down, probably. And so, as long as the angle between the measurement direction and the hidden spin direction is less than 90 degrees, I would call it up. At least that's a possibility. So if we take a measurement on particle A along this direction little a, then we just prescribe in our model that the result will be up if the angle is less than 90 degrees. Or I could just take the scalar product between the two, and if it's positive, then the angle, then it's up. So if you want to write this more formally, you could say capital A should be now the measurement result, which could be plus or minus 1, up or down. And it will depend on the measurement direction as well as this spin direction. And that I can define as the sine of this lambda times A. And I would do the same for B, obviously. And if you're asking me, what should I do if lambda times A is 0, I don't really care, because that's, as they say, a set of measure 0, it really never happens. And if it happens nonetheless, we can invent some prescription, but it doesn't really matter. Okay, so this is nice because it gives these discrete results, just like in the quantum case. And you immediately see that the sign of, if A and B are parallel, then the sign of lambda times A is just the opposite of the sign of minus lambda times B, obviously. So we know that they are opposite, that the results are opposite. So likewise, we have the result for B, given the measurement direction little b, and the same hidden variable vector lambda, and that is minus the sign of lambda times b, simply because here the spin is pointing in the direction minus lambda. So this is our simple model. And I guess it's hard to come up with something simple. And now we can check whether it gives the correct results. For example, I just mentioned that if A equals B, if the measurement directions are parallel, then we will always get opposite results. And that's nice, because that's just the quantum result. So if A equals B, then capital A of little a and lambda is always minus capital B of little b, which is now equal to little a and lambda. And so, yes, we get opposite spin directions just like in quantum mechanics. And then there's the other simple case which you can test. Namely, in quantum mechanics you can also have the situation where you measure in perpendicular directions. So, like you measure in the z direction for one of the spins and in the x direction for the other spin, then you can work it out very easily that since the measurement in the z direction will project both spins into the z quantization axis spaces, then the subsequent measurement in the x direction will just give 50-50. Because if I have prepared a spin, say, in the z direction up or z direction down, it doesn't matter, and measure along the x direction, it's just 50-50, one or the other, up or down. So let's see whether we get the same result here. Okay, so here it's best to draw the picture graphically. So I'm going to draw this unit sphere on which the lambda vector is going to lie, and it's uniformly distributed over the sphere. And then say A is pointing upwards. So I will get a +1 for the measurement result A whenever I'm in the upper half sphere. Okay. And B is just perpendicular to A, so B is pointing like in this direction. And again, I get a positive measurement result B if I'm in the upper half sphere with respect to this new direction, which would be that sphere. Well, it's supposed to be a half sphere. And now you see that, for example, if I'm in this quarter sphere, I will get both plus for A and plus for B in this part. And here I will get opposite signs. Here again I will get the same sign, here I will get opposite signs. So that means, since lambda is randomly distributed, I will just as often get plus plus or minus minus as I will get plus minus and minus plus. And so how could we express this? This is, by the way, exactly what happens in quantum mechanics. Half of the time they will be both up in the respective directions, half of the time they will be in the same direction, either up, up or down, down, and half of the time they will be up, down, down, up. So the easiest way to express this is just to take the average of A times B. And the average, of course, for this particular case will be 0, just as often positive as negative. And so, since we need this average in the future, I just write it down more explicitly. We would say, aha, what is the average of these quantities? Well, I can be more explicit in writing down the variables. These depend on the measurement direction and the hidden variable. So I will integrate over this hidden variable. I will have a probability density for it. This is just the density that describes uniform random distribution of the direction over the sphere. And then I would multiply by the product of A and B. So it's capital A depending on little a and lambda, capital B depending on little b and lambda. But for our case, we know it's 0. So there are no correlations, just like in quantum mechanics for this case of perpendicular axis. So this looks very good, right? We have started with the simplest possible model, and we reproduce everything that up to that point had been discussed with respect to the Bohm version of the EPR experiment. And then the crucial step of John Bell was to see and check whether it also works out all right if there's an arbitrary other angle between the measurement directions. Here we have just tested 0 degrees and 90 degrees. And let's see what happens for other angles. So let's take another angle and let's just also take this picture. Because if I take another angle between A and B, I will just rotate these half spheres with respect to each other. Then, for example, if the angle between A and B gets smaller, there will be a larger region where they give the same sign. So now I don't want to draw it in a 3D version, but just as a side view to be very explicit. And A is still pointing up. So all of this upper half sphere will be lambda times A larger than 0. And then B is just slightly tilted with respect to A, so like, for example, in this direction. And so the half sphere is also just slightly tilted. So this inner half sphere would be the one where lambda times B is larger than 0. And now we just have to estimate what's the fraction of the different cases. And we can do that geometrically, so the angle between A and B I will call theta. And then you see that this angle occurs at several places. For example, it also occurs here and here. And so we can ask, what's the fraction of places on the sphere where lambda times A and lambda times B give different signs? And these are just those and those little wedges. And so what's the fraction? Well, we can estimate this. It's just, this would be the full angle of 2 pi, and 2 times theta out of 2 pi, that's the fraction of cases where the signs are different. So again, theta is the angle between A and B, and if I want to have the fraction where the signs are different, that will just be 2 times theta, maybe I take the absolute value if it has a negative sign, and divide by 2 pi. So the fraction is really, the fraction of this is really theta divided by pi. And so now we can just evaluate this correlator A times B average. Okay. So first, let's take these cases where the signs of lambda A and lambda B are different. This is the fraction of those cases. And what's the result of A times B? Well, it's positive in this case, because remember B was the negative of the sign of lambda times B. So if the signs here are different initially, then the result for multiplying A times B, the measurement results, is positive. And then we have all the other cases, which is just the rest, 1 minus this probability. And they give minus 1. Okay. And so if we add this up, we just get so I can write it like this. Minus 1 minus 2 theta over pi. So in particular, if the angle is 0, we get back minus 1, which just expresses the fact that we already discussed here. If the axes are parallel, then the spins are always opposite. Okay, and now I just propose to draw this. So I'm plotting A times B average as a function of the angle between the measurement axes. And so really I only need to go from, say, 0 to pi. I don't need to go further. And since A and B, the values of A and B individually are just plus minus 1, this average will just be between minus 1 and plus 1. And as we said, for theta equals 0, it's minus 1, perfect anti-correlations. For theta equals pi, which is just the opposite direction, I get plus 1, perfect correlations, so to speak. And if theta equals pi half, that is the case of perpendicular axis, we already said it's 0. Okay, so that's the result for this model. We just interpolate between these cases, and it seems to be fine. And so the next thing we have to do is just to compare against quantum mechanics. Of course, at this point it would be surprising if this exactly matches quantum mechanics, but we would have to see. Well, okay, so now A and B are supposed to be the measurement results for my spin measurements at the two stations. And if I like, I can even turn them into operators, or I say, no, these are the values that the experimentalist gets. I don't care. So it's just A, B expectation value in quantum mechanics for the singlet state, for this particular experimental configuration. And so, what are the rules of quantum mechanics? Well, in order to get such an average over measurement results, I just should take the expectation value with respect to the state that I'm talking about, which is the singlet state. Now, I'm measuring the spin, say, of particle number 1 at station A with respect to axis little a. And we already said if I want to measure in an arbitrary direction, I should take the spin vector, so sigma 1, the spin vector for particle number 1, and should take its projection along the axis along which I want to measure. So little a times sigma 1. This, as we said, has eigenvalues plus minus 1. In a measurement, I will just get these eigenvalues plus or minus 1. Okay? And the same I do for the second particle at station B with another measurement direction, b times sigma 2. Okay. So the task is to calculate this expectation value with respect to the singlet state. And in principle, you could do it brute force. You would have sigma 1x, sigma 1y, sigma 1z, and so on. And there would be many terms. You can also be smarter, and I think this will be homework in the tutorials, because you can exploit that the singlet state is rotationally invariant. We already said that each direction is the same. So you can be smart and choose a coordinate system in which one of the measurement directions is actually, say, along the z-axis. Then this first part is just the z component of sigma 1, which makes it easy. And then you just have to evaluate the expectation value of the second spin, which then, however, will be in a z eigenstate. And so this is fairly easy, you can work that out. And the end result is also easy, it's just the scalar product between the two measurement directions, A and B. Yeah. So for example, if they are parallel and they are unit vectors, A times B is 1, so you get minus 1. If they are perpendicular, you get 0. So these are all the results that we already obtained. Now if I write it in terms of the angle between the two, it's of course, scalar product is the cosine of the angle. So this is the quantum mechanical result for the correlations between the spin measurements. And we see that does not quite fit our little model. Of course, we would have been surprised if it did, but it doesn't quite fit, because if I draw the cosine, I would get this curve. And so the only places where it matches are the ones we checked. And so this was quite a step in the discussion of the problem, because up to that point, people had always only discussed these very simple situations, where you get perfect anti-correlations or no correlations at all. They had never thought that something in between might be important. And for example, for the original EPR, this is not surprising, because you can say I measure x, I measure p, but it would be a little bit weird to come up with the idea of measuring a linear superposition of x and p, like 1/2 x plus 1/2 p in appropriate units. You can do that, you can think up setups where you do this, but it's not something that comes to your mind easily. Now, the spin setup, of course, there's more natural to say. I also want to measure the spin along different directions, but again, this was not, for example, discussed by Bohm. He just concentrated on these simple cases. Okay, so that was our simple model, and we could, of course, try to make more sophisticated models. One particular model could be the following. We would say, oh, I want to stay with quantum mechanics, but my source always emits along a definite quantization axis, up and down with respect to a definite axis. And then the next attempt also up and down, but with respect to another randomly chosen axis. So it's a little bit like our little model, but now the measurement you want to describe within quantum mechanics. So you just have a source that emits a statistical mixture of up and down with respect to different randomly chosen directions. That you can do, and you can calculate the result, and you find that the result is just 1/3 of the cosine. So it would be like up, down along z direction, up, down along different direction, and so on, emitting such a string of pairs of particles. But obviously there you don't even get the perfect anti-correlations, because, for example, if you measure along the z-axis, then you will get perfect anti-correlations for this particular pair, but not for the other pairs. And so you spoil the perfect anti-correlations. You reproduce the shape, it looks like a cosine, but you spoil the perfect anti-correlations. Now fine. This was only the simplest model, of course. Let's call it model, let's call this quantum mechanics. This was the simplest model, and you could try many others. I don't know how many Bell tried, if he tried any others, but after some time he seems to have noticed it just doesn't really work. In particular, if you want to get these perfect anti-correlations here, it always seems that you need to have this finite slope and never get this nice round shape of the cosine, so it simply doesn't work. You can get this round shape if you are willing to sacrifice the perfect anti-correlations, but then again, this is not what you want. And so, I guess after sufficiently many fruitless attempts, you get the suspicion that it will never work. And so then the question is, what do you do? How do you prove that it never works? And here there are probably many possibilities. For example, if I had faced this problem, I might have been tempted to say, oh, like I take the distance between my model and the quantum mechanical result, and then I take the average distance, and then I would try to prove that the average distance can never be zero, that there's always some distance between those curves. Or you could take the distance maximized over the angle and then prove that there's a minimum bound for that. But Bell did something smarter. He just proved something that does not refer at all to quantum mechanics. He proved a constraint that any such model has to fulfill, and then the idea is to insert the quantum mechanical result and show that the quantum mechanical result violates that constraint. So that is the idea. Now, in order to be able to prove something general, you also have to start with a general definition. You have to be more concrete with what kind of model you want to have. And when writing down this definition, we will just have in mind our very simple first attempt, and we just define the models we want to look at to be similar to the one that we already looked at. And so the name that people have for models of this type is not only hidden variable theories, but local hidden variable theories, and I will explain why that adjective comes about. And so the first ingredient obviously is a hidden variable. Which we traditionally call lambda. Now, lambda could be, for example, the spin direction, which is already a vector. Could be any other combinations of complicated internal properties. You could also imagine that around your particle you have some wave field in a complicated configuration, so lambda would then even be a full field, a wave field. It doesn't matter. It doesn't matter for what we are going to say. Then you assume that things are stochastic in the sense that the source can stochastically emit the two particles in different invariable states, lambda. Also, a part of the hidden variable lambda might more be relevant for the properties of particle number 1, another part may be more relevant for the properties of particle number 2. We don't care at this point. Okay. And then The measurement. The measurement is supposed to give only +1 or -1. And of course the measurement, and this is important, will depend on the measurement axis, the setting at the detector. So we will call them capital A, depending on little a and lambda. And again, this will be +or -1. And likewise capital B, depending on little b and lambda. And these little a and little b are just the detector settings. So for us it's the orientation of this Stern-Gerlach magnet. And now, why is this a local hidden variable theory? Well, we see that the measurement result at station A is not supposed to depend on the measurement axis little b. It would be strange if it did, yeah? Because they are supposed to be separated over a large distance possibly, and why should the measurement result at A depend on what setting you choose at detector number B? And likewise for capital B. So that's the reason why we call them local. Otherwise, really everything is possible. So it's called local because we don't allow the result to depend on the other detector. Okay. And now the idea is to just start from there and derive a constraint on the statistics. One constraint would certainly be that the expectation value of A times B is never larger than 1. But unfortunately, this constraint is also fulfilled by quantum mechanics, so it doesn't tell you anything. So maybe I'll write down again what correlation functions we want to look at, like A times B average. And it's defined in the way that we already wrote down. To integrate over all possible values of the hidden variable, weighted with a probability density, and then just take the product of the results. Now, if you want to derive a constraint that is really helpful, then we should probably have something where both the result for parallel detector settings and also for other detector settings is involved. Yeah? Because we already saw that you can have a trade-off. Yeah? You can have better anti-correlations, but then it gets worse at intermediate angles. So the result cannot just be about the value of A times B expectation value for a given set of settings. Yeah? So it has to involve several sets of settings. So when I say look at several settings simultaneously, I don't mean that you can measure along many different directions simultaneously. It just means that in your constraint, I want to have more than just this single product up here. So I want to have a constraint that involves many different angles. Now, here is Bell's original version, and it involved two settings, two directions for each of the stations. So we would call them little a prime, little b prime. If you look at the original paper, he chooses slightly different notation. This will make it a little bit easier also to compare against other results. I'm sure that if you go back to the original paper, you will easily find out the translation table. Okay, and now I want to make the notation as simple as possible just to show that this is really a very, very simple proof. So instead of writing capital A of A prime and lambda, I will just abbreviate it and say this is A prime. And likewise for all the other directions. Okay. Now, he picks a special configuration where he assumes that A prime and B prime are actually identical. They point into the same direction. And later we will generalize. Now, we know what quantum mechanics predicts if you have the measurement axis parallel. It's just perfect anticorrelations. And so he assumes that this hidden variable model also shows perfect anticorrelations. Again, this is something which we can generalize later, but at the moment this is assumed. And so in our notation, this would mean that A prime equals minus B prime always. They just give opposite results. So I would say for all lambda, this holds, regardless of how you choose lambda. Now the mathematician would insist to say almost all lambda, that is with disregarding a set of measure 0 because it has probability 0. Okay, anyway, so they are always opposite. And then we can have a very, very simple proof of Bell's inequality. So it's really only a few lines. Start with this one, A, B prime minus AB, and take the magnitude. Now, this is obviously the same as A times B prime minus B. Nothing happened here. And now A is just plus or minus 1, so the magnitude is always 1. So I can just say, oh, this is the same as B prime minus B. So A dropped out. And then I will use this condition. It has to go in somewhere. So B prime is minus A prime, so I get minus A prime minus B. I could also, because of the magnitude, say A plus B. A prime plus B. Okay. And now comes a little additional step. Let me just write it down. I claim this is equal to 1 plus A prime B. Now why is that? Well, you see, both of them are just plus or minus 1. Suppose both are plus 1, then this is true. Suppose both are minus 1, then this is also true. Suppose they have different signs, then this gives 0, but this also gives 0. So there are just 4 cases and you can just check them. Okay. And at this step, so this still holds for every possible value of the random variable. I still did not average. But now I want to average. I want to average this right-hand side of the equation. Okay, fine, so I will get the average of A prime B. This is one of those correlators that I'm talking about. I will also want to average this magnitude sign. But you know something, that the average of a magnitude is certainly larger than or equal than taking the average first and then afterwards taking the magnitude. Because if you take the average first, positive and negative contributions can tend to cancel each other. So what I will use now is that if I take the average of this, so the average of the magnitude of some x, then this is certainly larger than or equal the magnitude of the average of x. This is certainly true. And so now we can just write down the result, and this will be Bell's inequality. So this then is less than or equal to the right-hand side. And so that's Bell's inequality. So starting from this local hidden variable model, you can prove that there must be this constraint for the correlators. And so if you want to read this, it's hard to find the original paper because it was published in a journal that I guess existed only for a year or so. But you can look into this book where all the writings of John Bell have been collected, and it's called Speakable and Unspeakable in Quantum Mechanics. So I recommend this book because Bell is a very lively writer and has many funny side remarks. Okay, so that's an inequality that has to be fulfilled by any such local hidden variable model, given that we know that for equal settings, the results are perfectly anticorrelated. So that's a little constraint here. And then one of the generalizations that we are going to discuss just gets rid of this constraint and can just deal with the general case. Now, this is nice. This is a constraint. It looks more complicated than a simple constraint A times B average is less than 1, and less than or equal to 1. But the question is, of course, whether you can have a situation where quantum mechanics violates this constraint. Because if quantum mechanics always fulfills this constraint, then it's just trivial. It doesn't tell you anything. So then the trick is to find a situation where quantum mechanics gives something different, and I'm picking the configuration that Bell proposes. So you compare with quantum mechanics. Remember there A times B average is just minus the scalar product of the measurement axis directions. And now I just have to pick a certain set of measurement axis directions. And I have to be smart. You know, they can't just all be parallel, because then it will be trivial. And so here's the choice of Bell. You would have like little a and little b perpendicular. and little a prime and little b prime were supposed to be parallel, that we already said, and you choose them just in the middle with 45 degrees. And then we can check what quantum mechanics gives us for this situation. And afterwards we just insert there. So, for example, if I take A, B prime according to quantum mechanics, what is this? A and B prime have this 45 degree separation. So the cosine is just 1 over square root of 2. And I will get a minus sign because of this. Okay. Then AB, what is that? Well, since they are perpendicular, it's completely uncorrelated, it just gives 0. And then finally, A prime B. Again, A prime and B, it's 45 degrees, I get minus 1 over square root of 2. And so then I can insert into the left-hand side, A times B average is 0, so all that remains is this one. And on the right-hand side, here I get 1 minus 1 over square root of 2. But now the trouble is that if you compare, the left-hand side is not smaller, it's rather larger. So it's not smaller as predicted by the Bell constraint, but rather larger. You can see this, for example, if you multiply by square root of 2, and then on the left-hand side you would get a 1, and here you would get square root of 2 a minus 1, but square root of 2 is about 1.4, so the difference is 0.4, then 0.4 is certainly smaller than 1. And so this is a clear result where the quantum mechanical correlations simply do not fit the local hidden variable model. And so by this equation you know, however hard you try, however clever you are in constructing your local hidden variable model, you will really never make it work. You can have compromises, you can get better at one angle, but then you will get worse at another angle. And so that's what Bell tells us. So one thing we have to notice is that Bell's inequality at first doesn't tell you whether local hidden variable theories work or don't work. It just tells you that they seem to be in conflict with quantum mechanics. So unless you do an experiment, there's still the logical possibility that the world is really described by local hidden variable theories, and that would have to mean that quantum mechanics fails, at least in such situations. It's possible. It could be that quantum mechanics works for a lot of situations pretty well, and the failure just becomes apparent in such situations. This is completely possible. So in order to really rule out local hidden variable theories based on Bell's theorem, you really have to do experiments. And so later, next week, we will actually discuss the various experiments that have been done. Also, I want to point out the irony of the story with respect to the original purpose of the Einstein-Podolsky-Rosen paper. Yeah? Because you remember, they said, okay, let's suppose quantum mechanics correctly describes the results of such a Gedanken experiment, a real experiment with two particles. Let's also claim that there can be no spooky action at a distance, and so from these, by way of the argument that we discussed, we conclude that yes, probably there must be hidden variable theories. And now things are really turned on their head. So let me just summarize this, because now you say, oh, if I do have, if I insist on having a hidden variable theory, and I also insist that the results of quantum mechanics are the correct predictions for such an experiment, then what Bell's inequalities tell me, this hidden variable theory cannot be local. Because otherwise there would be a conflict. It must be non-local, so there must be spooky action at a distance. So this is certainly not at all what Einstein-Podolsky-Rosen would have liked to be the result. Or if you insist that there is no spooky action at a distance, then you cannot possibly have both the hidden variable theory and the quantum mechanical results. You could still hope, in the absence of experiments, to just the experiments to violate quantum mechanics. That's still a possibility. But if that then is not borne out by experiments, you're really in trouble. Okay. So this is not at all what Einstein, Podolsky, and Rosen would have liked to have. Now, there is still room for improvement with regard to the Bell's inequalities, because, for example, here you make the assumption that for this particular parallel setting you have perfect anticorrelations, but maybe in the experiment it's just 98% anticorrelations. So then, in principle, you are not allowed to apply this reasoning. So it would be better to have a constraint that does not make this assumption. Another shortcoming somehow is the following. We always assume that the measurement results will be plus or minus 1, up or down. But sometimes in the real experiments, the detector will not click. For example, because the photon has been absorbed somewhere else. And so there will be no result, neither plus 1 or minus 1. And so you don't know what to do. And so the reasonable thing to do would be to say, oh, then the result is 0. So that changes things a little bit. And so you would need new inequalities that also work if the detector is not quite as efficient. And this generalization that incorporates all of this was then provided a few years later, and it was provided by 4 people, Clauser, Holt, Horn, and Shimoni. And so this is then the modern version that is actually used to describe experiments. And the derivation is actually at least as simple as for Bell's original proof. So, as I said, we also want to have the ability to have a detector that doesn't fire, which is just the result 0. And otherwise the setting is the same. Again, we imagine that we have at least 2 different directions, and I will call them A and A prime, the corresponding measurement results. And there will also be 2 directions at B, that will be B and B prime. So the setting is just I have 4 random variables, A, B, A prime, B prime. They can be not only plus minus 1, but also 0. And they are random variables in the sense that, in the way discussed before, they depend on this random hidden variable. Okay. So more we do not know, we do not need to know. Okay, so here's the proof. So consider the following combination. It looks a little bit similar to what Bell did originally. So you have AB plus AB prime plus A prime B minus A prime B prime. Okay, so the difference is that first there's a different sign, and second here it's A, that's A prime. Okay? Now, if A were just plus minus 1, then this whole thing would just be equal to the magnitude of B plus B prime, just like previously. Now A can also be 0, in which case the whole thing vanishes. So instead of writing an equal sign, I will write less than or equal. Okay. So it's the sum of these 2 terms, B plus B prime and B minus B prime. And now, well again, in principle you don't have that many cases because it's just plus minus 1 or 0, so you could just go through all the combinations. Or you can just have a look at it. So for example, if both are 0, everything is 0, fine. If only one of them is 0, like for example B prime, then you get B plus B, and if B is non-zero, that just gives you 2. If both of them are non-zero, for example, they have the same sign, then you get 2 here, but 0 there. If they have different signs, you get 0 here, but 2 there. So it never goes beyond 2. Okay. Well, now you can guess what I'll do next. I'll just take the average and use this old inequality that the average of the magnitude is larger than or equal than the magnitude of the average, and then we're done. So then we get the Clauser-Bolthorn-Shimony inequality. So this is the inequality which people nowadays use to interpret these experiments. And so this now really holds for any general local hidden variable theory in the sense we define. We don't need to make this extra assumption that for parallel measurements we get these perfect anticorrelations. We can also have detector inefficiency, it doesn't matter. So of course, when I say it doesn't matter with respect to detector inefficiency, it means you can tolerate a little bit. It doesn't destroy the concept. You would just assign the value of 0. Of course, if there's too much of 0 in these averages, then all these numbers tend to be very small, and then they won't ever violate this inequality. So that's the trouble with inefficient detectors. Okay. Now, the way I described it, it seems I just need 4 random variables, which I call A, B, A prime, B prime. They have to take only the values -1, 0, and 1, and then I can always derive this inequality. So where do I get the locality? Where is the locality hidden? Let me note that. So the locality is really because we assume that whenever I write A times B, this of course is a shortcut to say the result at A for measurement axis little a and the result at B for measurement axis little b. Whenever I write something like A times B prime, it's the shortcut for the result at A for measurement axis little a, but also now the result at B for measurement axis along B prime. And the assumption is that the A that occurs here is just the same A as occurs there. It does not depend on the fact that here the setting is different for the second station. So again, A of A lambda, assume independent of the setting of the second detector. And so that means if I write A times B, this is really A of A lambda, B of B lambda. Whereas if I write A times B prime, this is the same A of A lambda times capital B of B prime, comma lambda. Yeah, so it's a little bit hidden in there. So that is what locality means. What I do here, what I measure here, cannot possibly depend on the other detector setting. And the way to enforce this in experiment, if we believe relativity, is just to make sure that there was not enough time for a light signal to reach our detector station in the time that it needed to do the measurement. Okay. Good. So are there any questions right now? Well, if not, then I guess we continue on Monday.